Okay, so it's time to start. Thank you for coming. And this week's topic is about fair division. So we are still in the theme of applications of mathematics in social sciences like politics or economies. And today the topic is also related to something like politics. Okay, so we are going to talk about divisions, right? So there are two kinds of properties. One is you can divide things in an arbitrary way. The other one is there are some objects you cannot divide them. If you divide, it's broken. So today I will talk about the case where things can be divided. And on Friday we'll see what to do if you cannot divide them arbitrarily. Okay, so well, there are quite a number of items, but each item is an algorithm. So I will introduce an algorithm for some situations, and then I'm going to convince you that the algorithm will work. Okay, so first I will say something, and then I'll introduce 5 algorithms about division, fair division. Okay, so the motivating question, the overall question is very easy. So here, is there a best way or ideal way or optimal way to divide a collection of things or objects among a group of people so that everyone is satisfied? Right? Suppose I have something here and then I want to share with everybody, and is there a way to divide the things so that everybody is happy, right? So this is the question. So obviously in real life, we encounter many examples like this. So for example, okay, so between countries, you can talk about division of territories, right? So after World War II, Berlin was somehow divided, and now it's still, there are certain area in the world like Kashmir, and then somehow it's still divided. Okay, so, and also division of assets, right? For example, in a divorce case or company mergers. So after 2 companies merge, and then they are going to reallocate the departments. So there is an issue of which company gets what part of the outfit, right? So there's a division of assets in this context, and also division of inheritance and division of bandwidth, time, and so on and so forth, and division of natural resources. So there are lots of examples of divisions. Okay, so now this topic, fair division, actually has a not too long history, right? So it was developed in 1940s, near the end of the war, the Second World War. So it was devised by a group of Polish mathematicians, Steinhaus, Knaster, and Banach. These people, they are famous for other reasons. Like if you took any mathematical course, you probably know that Banach is a famous analyst, right? In a functional analysis, you'll hear the Banach space and so on and so forth. So these people are mathematicians, and they work on real pure mathematics. But somehow they are interested they get interested in the fair division problem. So in particular, in 1944, that Banach and Knaster developed some algorithms we are going to learn later today. So it is quite interesting. Okay, so now this topic actually is an active research area in mathematics and economy, and especially in social choice theory. Right? So last week we were talking about voting. That's part of social choice theory. And today the fair division is also part of social choice theory. Okay, so that's a little bit history. Now, we want to make the problem slightly more clearer, right? Slightly more rigorous or more precise defined. Okay, so first let's look at what are the possible difficulties. So a key point here is that different people in a group may value the parts of the collection differently. Right? We want to divide a collection of objects. Now, in different people's mind, they value the things differently. So, is it possible to satisfy everyone? So that's the problem, right? So, in other words, okay. So let's say what is the meaning of value things differently? So, in other words, we are allowing subjective valuation, right, as opposed to objective valuation. So what is objective valuation? So that's very simple. So suppose we have 10 $1 bills, right? Suppose you are dividing 10 $1 notes between you and your friend, and each will get 5, right? So $5 is $5, right? Now it has a objective value, right? And also it doesn't matter which particular $1 bill you get. So you get 5 notes, then that's it, right? So in this case, it's very easy to achieve the fair division, right? Each person just get 5. Now, how about these subjective values? And then different people may have different opinions, right? So let's look at one example. Okay, so for example, there's a cake. By the way, in today's lecture, we are going to talk about lots of cakes because cake is a typical example of things you can divide, you can cut, right? Okay, so here, so suppose the cake has 2 portions. One is mint, one is strawberry, right? Mint, chocolate or whatever. So the total value is, let's say, is $12. Okay. So now different people may like different flavor, right? For example, Anne she may value it in this way. She would think that the mint chocolate is like $6, worth $6, and strawberry part also worth $6. So Anne will view it like this. Now, Bessie, she doesn't like mint chocolate, so she valued the green part less. So she would think that this is the mint chocolate part only worth $3, and then the $9 goes to the strawberry part, right? So there are different valuations. Now, is it possible we divide the cake and satisfy both of them? Okay, so we'll come back to this problem in a moment. So this is the easiest example we are going to have. Okay. So now I want to repeat what I just said. So the objects can be of different types, right? So and the difference may affect how we divide them, right? So the most important difference is divisible and indivisible, like I just said a few minutes ago. So here, the divisible means, so the divisible also called continuous. So it means the object can be divided in a continuous way. And shares can be increased or decreased by arbitrary small amounts, right? So you can trim a little bit, you can add a little bit, or it's like, I don't know, it's like a container of liquid, right? You can divide it in arbitrary portion, right? So in this case, we call it, some people call it continuous, and we just call it divisible. It's just you can always cut small portions and adjust the value a little bit. Okay. Now, the typical examples we are going to use are actually, we only use cakes, or there's one example, we use land, but they are all artificial. And pizza, okay, so pizza is like a cake, but somehow pizza have different toppings, and some people, in some book, people use pizza for non-divisible. But anyway, so we are not going to use pizza in today's lecture. Okay. Now, on the other hand, the indivisible, so this is also called discrete. This is a mathematical term, discrete. So the meaning the value is lost forever when divided. For example, painting, right? So there's a piece of painting by Van Gogh, right? So if you cut them into pieces, then it's not valuable anymore, right? So you cannot cut paintings. And houses, right? All these things are, it doesn't make sense to divide it into arbitrary small portion, right? So the value will change. Most likely is getting smaller and smaller, right? So we are going to talk about division of these indivisible case on Friday. Today we are going to talk about divisible cases. And also there's a homogeneous or heterogeneous, there's a difference between these two kinds. For example, the homogeneous, suppose you have a bunch of money, you have lots of money, and you divide money, just divide the number, right? Now, if you have different items, like you have, you inherit something, like some of them maybe car, or some of them are houses, and then there are different things, right? It's not easy to allocate them. So we are going to see one example of this sort later today. Okay. And the last one, we are not going to see it at all. So it's desirable, undesirable. So when you talk about fair division, sometimes the object allocated to you is not a reward, is a punishment, right? So in the negative case, there's also the issue of fair division, right? So if you want to divide something negative, undesirable things to people, then you probably need to consider these things. But we are not going to, not in this GEM module. Okay, so today we are going to talk about divisible case. Okay? Okay, so as in the game theory, we have to make some assumptions. So we assume the players or the person who is going to get these assets, they are rational and they play fair. Okay, so this is reasonable. And also, there is a privacy assumption. So it says they have no priori information about the likes and dislikes of other players. Right? Different people value things differently, but the player may not know how the other people value things. Right? So there's a privacy assumption. And also, we assume all players have equal rights in sharing assets. So in other words, if there are 3 players, each player is entitled to at least 1/3 of the assets. So in textbook, you can consider, you can divide things in a different portion. For example, maybe 2 of us buy a pizza, and he spent $10, I spent $5. So we do not deserve the same amount of share. So in that case, you have the issue of not the equal right, right? So, but again, this is a GEM module. We only consider the case where all players have equal rights. Okay, so we divide things evenly. Okay. Okay, so some mathematics, but okay, so the purpose of this slide is just to make everything precise. But in the later argument, we seldom refer using these terms. So we use daily, the usual terms. But to make everything precise, let me introduce some terminology. If you don't like it, fine, you can forget it. Okay, so the general setting is we have a set A of assets. Right? A may be the set of, it consists of one house, one car, and one TV, one something. Okay, one computer. And, okay, so the set A is the set of assets you want to divide. And there's a group of players, N players, is called capital X. So this is person 1, person 2, up to person N. Right? They are going to share the asset capital A. Okay, so now each player has her own valuation, right? So assume that each player K, so here, player K here in the collection of X has her own valuation of bundles of the assets, as we assume by the privacy assumption, only she knows how she values things, right? So there is a function, the valuation function, with a subscript K indicating this is the opinion of the case player, right? So the case player will assign a number of the items in the collection, right? So for example, just now I said A consists of a house, a car, so maybe the VK will value the house like $1 million, a car, I don't know, 100,000 or something, right? So you can give every item a value, or you can give a collection of items a value. Okay, so usually the value is a real number. Okay, so that's your valuation function. Now let's assume the total valuation is 1, right? Just okay, we can normalize it, right? So even if it's not 1, the total number is finite. You can just divide them, make it 1. Okay, so suppose everybody value the total collection of value 1, and these functions are so-called additive. In other words, if you have two disjoint subsets of A, and then if you add the value individually, if you evaluate them individually, then add them up, is the same as you put them together, give a total valuation, right? So this is a reasonable assumption. Now, our goal is to divide the asset A into disjoint union of A1, A2, AN, right? And then we give A1 to player 1, A2 to player 2, and AN to player N, right? So giving AK to player K. So this is called an allocation, right? This is as the name suggests. So each player, so our goal is to achieve the thing in the quotation mark. This is the most difficult thing, right? So we want to make everybody happy. So each player is satisfied. Now the question is, how do we define satisfaction? Okay, so we add two conditions. So there are two common measures of satisfaction, right? So one is called proportionality, right? So it says an allocation is said to be proportional if each player K feels that she received at least 1 over n of the value, right? Because everybody has an equal right. So everybody will think they deserve at least 1 over n, right, of the total value. So in other words, using her subjective valuation, she will value the portion she gets bigger than or equal to 1 over n. Right? This is proportional. This is considered a fair division. Right? So this is one condition. Okay. Now the other condition is so-called envy-free. So an allocation is said to be envy-free if each player K feels that the piece she received has greater value in her own valuation than the pieces others receive, right? So that she does not envy the other players, right? So not only she got what she deserved, right? She would think nobody get better, right? So in mathematical terms, this means the player K will value the portion she got, AK, bigger than or equal to other portions, right? So here the AR is the player R, is the collection player R received, right? So player K will think what she got is at least as much as the player R got, so that she does not envy player R, right? Is it okay? So the purpose of introducing these VKs are just to introduce these two terminologies. If you don't like the VK and so on and so forth, you just think proportion as proportional, as she got at least 1 over n. And then the envy-free, you can think of it as nobody get better than what she gets, right? So are these two things clear? In the next hour, we are going to concentrate on these two things. So I hope this is clear. Okay? Okay, so now to test our understanding, right? So let me ask you, right, do you agree with this? So envy-free allocation implies proportional allocation. Is it true? Okay, let's see, right? So we want to we gave a mathematical proof. We want to use a contrapositive, right? So I want to convince you this item. So I do the contrapositive. So I want to convince you if it's not proportional, and then somebody is going to envy. So it's not envy-free, right? Okay, so let's see. Suppose it's not proportional. Okay, last slides I already defined, right? Proportional means the player K will think she gets at least 1 over n, right? So now if it's not proportional, then there will be a player. The player will think what she got is strictly less than 1 over n, right? So this is the definition. And then look at the other parts. So the player K must think some other AR worth more than 1 over n, right? Because otherwise you add the total is less than 1, right? If everybody get less than or equal to 1 over n, and then player K gets strictly less, it doesn't balance up. If you add everything, the total will be less than 1, right? Somebody must get more than 1 over n, and then player K will envy that player, right? Although the valuation is her own elevation, but she will envy player R, okay? So therefore, if it's not proportional, then somebody is going to envy. Now, take the contrapositive, it says envy-free allocation implies proportional allocation, right? So the consequence is envy-free is harder to achieve. Right? You may achieve proportional, but it may not be envy-free, right? So envy-free is harder. If you achieve envy-free, then automatically you achieve proportional. So keep that in mind. Okay. Now, however, in a special case, suppose there's only 2 players, and then these 2 concepts coincide. So envy-free is proportional, proportional is envy-free. I'll leave this for you to think. It's easy. Okay. Okay, so can we move on? Okay, so now that's the introduction. So now we talk about what should we do, right? So we are having some asset in front of us. Can we give a decent plan or decent algorithm to solve the fire division problem? Okay, so let's look at the simplest algorithm. So we have 2 persons, and the object is divisible. You can cut in whatever way you want to cut. Right? Okay, so there's a name called this. It's very suggestive, called divide and choose. Okay, so the simple case is the following. So we have a divisible object. Let's assume cake is divisible. So we have a cake in front of us. Now we want to divide them between 2 players, two persons, A and B. Okay? So here's the algorithm. It's called divide and choose, just like the name suggests. So we will ask one person to divide them, like ask A to divide the cake into 2 portions, in whichever way she prefers. Okay? But we let the other person choose which portion she wants. Right? So one person divide, the other person choose. And then the remaining part goes to the divider. Is the algorithm clear? Okay. Very simple, right? Just 2 lines. Okay. Now, let's argue that this is a good algorithm. So remember that for 2 players, envy-free is the same as proportional, right? So now I want to convince you the result is envy-free. Okay? Is it true? Is it envy-free? Well, let's try, right? Who is going to envy? Is player A going to envy? He's a divider, right? So he knows, he or she, whatever, okay. So the person, Mr. A, knows B is going to choose first, right? So definitely she will not risk okay, she'll try her best to cut the cake equally, right? Otherwise, because B is going to choose first, B would choose the better part otherwise, right? So because A is a divider and she knows B will choose first, so A must divide in such a way that she can accept any one of the pieces. In other words, she must cut it in her eyes evenly, right? Is it clear? So she won't get envious. Now B, can B get envious? No, because B is the person who chooses first, right? So there's no reason that she is going to get envy. So both A and B are happy, right? So this algorithm works, okay? Now is there an issue? Well, there's a small issue. It's not about fair division, but so here's a small issue. So the issue was the divider certainly get roughly about 1/2 of the value of the assets, but the chooser has a potential advantage. So the chooser may get more than half. Why? We are going to see in the next example. Okay. So the divider, in her eyes, she already cut it evenly, so she doesn't care. But in many situations, the chooser may have some advantage. as the example will show. Okay? And another limitation is not about, so it's about the nature of the asset. So we emphasize that this only apply the asset can be divided. It's a continuous or divisible assets. If it's a car, then you cannot use this method to divide. Okay. All right, so example, right? So look at this. So we have seen the top part, right? So there's a cake worth $12, and then Anne and Bessie want to share them. They have different valuations and so on and so forth. Now we apply this divide and choose algorithm. So we ask any one of them cut. Okay, so maybe Anne cuts. Okay, so Anne will cut the cake because in her eyes the green and the red are equal. I mean, so any line passing through the center is fine for Anne because no difference for her, right? So she'll cut, for example, like this. Okay, so therefore, I mean, on the to the left is $6, to the right is also $6 in Anne's point of view. Okay, so Anne cut this way. Now, obviously, from Anne's valuation, both are acceptable to her because to the left is $6, to the right is also $6. So to her, she can accept any pieces, okay? And then come to the chooser. So Bessie will choose, right? Now Bessie, she likes the strawberry part, so she'll choose the portion with more red, more strawberry. So she'll choose something like this. Okay? So then Anne gets the other part. Okay? So this is envy-free, right? Because Anne gets $6 in her view, so she doesn't envy the other piece. The other piece is also $6. Now, Bessie had some advantage, right? So this is what I said. So she will get actually, in her valuation, she get $7. Is it? Okay, so here we have 6 and 1, right? So certainly she is not envy Anne, right? So this is the example illustrating the divide and choose algorithm, and also illustrate the point the chooser may have some advantage. Okay? Now the question for you is, how about we let Bessie divide and Anne choose? So you can suggest some plan, right? So one possible way is just cut through middle, right? So you cut it here, and then Anne will choose whatever side. Okay. Now it's also possible that because Bessie think strawberry worth more, so I don't know, maybe she'll cut like this. So in this part, although the size is smaller, right? This $6 part, but to Bessie's valuation, this is already worth a half because the green part is cheap, right? So if Bessie does this, and then Anne would have an advantage, right? Anne would get all the green part together with this small slice of strawberry. So in Anne's evaluation, she will get $8 because the strawberry will, sorry, the mint part is $6, and the slice of strawberry also get $2, right? In Anne's evaluation. So in other words, I'm repeating that the chooser may have advantage. Okay. But it's not of our concern. This is a fair division already. It's envy-free. The problem solved. Okay. So that's the simplest case, 2% divisible. Now, how about 3%? Right? So first, I want to say the most naive way fails, just as you expected. Right? So let's just spend 1 minute on this. So the naive way of one person divide and other two person choose in turn does not work. Right? This is quite obvious. Okay, so quick example. So suppose I have one divider, two choosers. So unfortunately, you have to give an order for somebody is a chooser 1, somebody is the unlucky one is a chooser 2, right? So the divider will, in her valuation, will divide things evenly, 1/3, 1/3, 1/3, for sure, right? That's no problem. Now, the pieces in the eyes of the chooser may have different valuation. So maybe chooser 1 will think 40%, 30%, 30%. And chooser 2 think this, right? So it's possible. Now, if we do this naive, right? Naive means we don't think too much. And so the chooser 1 certainly go for the 40%. And then after chooser 1 pick the 40%, chooser 2 can only have 30 and 25 to choose. And then is in her eyes, this is not fair. And she will envy, and we have lots of trouble, right? So the naive way doesn't work. Okay. Right? So, okay, so now, is there a better way? Well, certainly, yes. And then this is the Polish mathematician, Steinhaus, in 1940s, gave this solution. So now it's called the Steinhaus proportional procedure, right? So it has another name called the lone divider. You'll see the reason. Okay. So the context is 3 players, divisible assets. Okay. So here's the algorithm. Okay. So now you need a little bit more attention to understand this. Okay. So let's consider 3 players, A, B, C, right? Anne, Bob, and Carol, or whatever. Okay. So randomly choose a divider. So this is a lone divider. So choose one. Choose a divider, one of them. Let's say Bob. Okay. So it doesn't matter. Okay. So he divides a cake into 3 pieces, X, Y, and Z. To him, each of them worth 1/3, right? Divider always does this. Okay. So then we ask N to indicate or approve which of the 3 pieces she finds acceptable, and also indicate which she does not approve. Right? So there are 3 pieces in front of N. And N can have different valuations. So which one she believes she can take, right? She believes is good, and which one is bad in her valuation. Okay? So N will indicate some are good, and maybe some bad, maybe some are okay. Right? So, and notice that N must accept at least one of the pieces, right? Because if she thought all of them less than 1/3, the total is less than 1. It's not, it's out, right? So it's not rational anymore. So at least one will, N must accept one piece. Okay. And then we ask the third person, Carol, to do the same thing. Okay, approve one or disapprove, and so on and so forth. Okay, so is it all right? So then there are 2 cases. After A and C did this, there are 2 possibilities. One is there are 2 pieces, let's say X and Y, such that A accept X and C accept Y. Right? So the 2 persons choose different pieces. Okay, if that's the case, problem solved. If that's the case, then the remaining piece Z will go to the the divider, right? And then A and C will get, A will get X, C get Y. Fair. Because each of them approved, say, I can accept this. So, okay. Okay. Now, what about this doesn't happen? What does it mean? It means A and C pick the same piece, right? The first case is A pick one piece, C pick another piece. Now, if this doesn't happen, it means A and C pick, approve, or accept the same piece, right? Let's say X. Okay, so there's the one only, then there is an only piece called X accepted by both A and C. Whereas the Y and the Z are rejected by both of them. Okay? Now, in this case, give Z to the divider, right? And ask and Carol to play the two-player game, but with the piece X union Y. Right? So here we use the divisible, I mean, the cake is cut and you can put them together, no problem. You can still continue to cut, whatever. Right? Do you understand the algorithm? It's wordy, but right? Now, why this is proportional? Okay, so let's see. So we claim that in both cases, everybody is satisfied. I mean, everyone gets a piece he or she accepts. In other words, the allocation is proportional. So let's see why. Okay. In scenario A, this is clear. Why? Do you still remember scenario A? This, right? So N accept X, Carol accept Y, and Z goes to Bob. Is everybody happy? Yes, right? Because N is happy because he approved X. C is happy because he approved Y. And Z goes to Bob because Bob is the divider. In his eyes, X, Y, Z are the same, are 1/3. So in the case A is obvious. Now how about B? In case B. In case B, the divider again is definitely happy because right, he cut in a way so that he accepts any of the pieces. So now he gets Z, so he's happy. Okay. But how about A and C? So the key observation is, okay, in scenario B, that they are going to play the game again. They are going to put X and Y together and redivide, right? So the key observation is, now, since A and C both reject Z, because they only favor the X, right? All others they think is too small. So they reject Z. So the reason they reject Z must be they think Z's value is less than 1/3, right? That's the reason they reject. So therefore, the remaining part, which is X union Y, is strictly bigger than 2/3, right? So therefore, when they play the two-player game, in front of them is a cake of value bigger than 2/3. So whoever gets, so remember the two-person game is proportional. So they will get at least half of it. So in the end, they will get at least half of the 2/3, which is 1/3. So they are going to be happy. Okay? So this is the proof or argument Steinhaus algorithm works. Okay? Okay, how about more than four player or more? Right, this algorithm only applies for 3 players. And how about more players? So I don't know whether this is accurate. So the London goes or internet says Steinhaus couldn't find a solution, So he passed the question to his students, Banach and Knaster. And these are now famous mathematicians. So they solve it. So it is called the Banach-Knaster proportional procedure. And it is more often called the last diminisher algorithm. You will see that this is really, this really helps us to remember the algorithm. Okay? So, so the Steinhaus method, actually, his idea actually works. So in 1960s, someone called Kuhn extended the result to arbitrary n. But somehow it depends on, he used some combinatorial theorems called Frobenius-Kuhnisch theorem. We don't care what it is. So if you use some deeper mathematical result, you can generalize Steinhaus algorithm. Okay, but it's beyond our syllabus. Okay, so now we are going to introduce this the last diminisher algorithm for these divisible objects. Okay. Now you need to pay even more attention. It's getting more and more complicated. Okay. So here is the algorithm. It's called last diminisher. Okay. So we have n players, right? So we have more than 3, 4 or more. So ask them to line up. Okay, 1, 2, 3, 4 to n. Okay. Now player 1 will ask player 1 to cut off a piece which he thinks has value 1 over n. Right. So here's a cake. Player 1. He'll cut a slice. In his eyes, that's 1 over n. Okay, so cut this piece, player 1. And then he pass to player 2. Okay. Now player 2 can have 2 choices. So player 2 can choose to do one of the 2 things. Case 1, the A. If she thinks the piece is of value less or equal to 1 over n, she pass it. Right? So player 1 give her a piece of cake. Then she thinks it's lousy, it's too small. I don't want it. Pass. Right? So this is option 1. Option 2 is she thinks the piece is of bigger value. Actually, the piece are good, too fat. Right? So she thinks the value is bigger than 1 over n. And then she is going to diminish. She can trim it down to a piece of value 1 over n in her view, and then pass to player 3. Repeat, right? Okay. Player 2 get a piece of cake, right? So in her mind, is this too small? If it's small, pass it to the next player. Now if it's big, big means bigger than the portion, then she will trim it. She will make the slice smaller to the size that she thinks is exactly 1 over n. Right? Trim it, then pass the trimmed case to player 3. So 2 choices, pass or trim. Okay? Okay, so that's player 2. Player 3 does the same. Pass or trim and pass. Okay, to player 4 and so on and so forth. Okay, until you pass n steps. Each player does this. Okay? And after the piece pass through the n person, the line, so the last person who trims it get the final trimmed piece. Right? And then the reason is because he feels he gets exactly 1 over n. Right? Because he is the last guy who trim it. The degree he trim is he trim it until he think this piece is 1 over n. And then nobody touch it later because he is the last diminisher. So he will get that piece. Okay? And then we have one piece less and one person less. So the n-1 people will repeat the same game to divide the remaining cake. Okay? So that's the last diminisher. Right? So the name actually is quite suggestive. Right? Okay, so now I want to argue that this is correct. So this division is proportional. Okay? Why? Because sorry. So first let's finish the thing. So we have one person less, right? We have n-1 player left, and each of them thinks the remaining cake is of value bigger than 1 minus 1 over n, right? Because the person after it will think it's less than this, right? Otherwise, they won't pass. The person before the last diminisher already done his job, so again, this is true, right? So here I wrote reasons. Okay, so the reason is if a player passed, then it is because she saw the piece was too small, right? So the remaining piece certainly bigger than this. If a player trimmed, then the piece after she trimmed, I mean, the piece that left her hand is already of length 1 over n, right? But since she was not the last the diminisher, someone later is going to trim it further, so the value is definitely less than 1 over n, right? So the last diminisher get the piece is definitely of value less than 1 over n to other players, right? So this is what I'm trying to say. Okay, so then we ask the n-1 player to repeat this pass and trim game, and so in the second round, last person will get 1 over n, sorry, 1 over n minus 1 of the value of the remaining cake. So he get this portion, but the total value is this. So together is 1 over n again, right? So in the second round, the person who took the piece also get 1 over n in his eyes, and so on, right? Repeat, and it's the same. So everybody gets proportional. Okay. Okay. So here's a example, but very artificial. But let's quickly go through it. Then we can take a break. So this is. So suppose we have 5 person. The 5 person want to split a piece of land. This is a land. So there is C, right? Okay, so here round 1, player 1 just take a piece, this rectangle, and then he passes to the next player. The player 2 will so he passes, right? And then player 3 think this is too big, so player 3 chop off a corner, say, this, in my eye, this is the right portion. Okay? And then player 4, okay, again, player 4 thinks this is too big. So he cuts off the other corner. So this is the right portion. And then player 5 say, pass, and this is too small. Okay, so the last diminisher gets the land. So player 4 is the last person who trim. So player 4, P4, get this piece, the red piece. Okay? So then there are 4 players, so 4 players to divide the remaining, the white area here. Okay? So again, we start from player 1. Player 1 will draw an area, this light blue area. So player 1 claim this is the right portion. Okay, then player 2 pass, right? Player 2 always pass. So player 3, okay, too big, cut off a corner here, cut off. and player 4 is already gone. So player 5 say, okay, he thinks this is too small. So the last diminisher, player 3, will take this, the light blue piece, right? And then there are 3 players. Okay, so it come to round 3. So again, P1 going to take a piece, this time green piece, and then P2, P5, let's say, passes, then P1 will keep this green. Now only 2 players, P2 and P5, so they are going to do this choose and divide and choose, right? So then finally the land was divided, right? So that's an example of last diminisher. Okay. So let's take a break. After that, so before the break, so here the question. So the last diminisher is called a proportional procedure. So we argue that this is proportional. The question for you is this envy free? If not, can you think of an envy free algorithm? If you can think of it, you are as famous as Banach. And, okay. So take a break. After that, we'll see how to make it envy free. Okay. Okay, so is this MV free? No, right? So the okay, so this is proportional. We just argued, but this is not MV free. For example, let's see P4, right? So after player 4 got this red piece, right? She cannot choose. She has no control of the remaining parts, right? So she may think that, for example, P3, this light blue is bigger than the red, but she already gets her part, so she cannot choose, right? So it's possible that player 4 will envy player 3, and actually she may envy everybody else. So, any case, anyway, so let's. So this is proportional, but not envy. And okay, so the title for this slide is from proportional. We want to get envy free. Okay, so the divide and choose for the is envy free, but it is only for 2 players, right? So then we see 2 algorithms. This Steinhaus and also this last diminisher. Both of them are proportional, but may not be envy free, right? So this is again not envy free. Now in 1960s, Selfridge and Conway independently come up with a envy free division procedure for 3 players. Okay, and they didn't publish this, so they just tell people that they have a solution. Okay, so now let's talk about their algorithm. Okay, then you need even more attention for this. Okay, so 3 players. Okay, we want to have an algorithm so that if we follow the algorithm, we'll get envy-free division of the cake. Okay? Okay, so player 1, player 2, player 3. Okay, so player 1, so there are several rounds. Okay, round 1, so player 1 will divide the cake into 3 equal parts in his view and pass them to player 2. Okay, this is as usual, right? So cut into 3 pieces, and player 1 can accept any one of these. Okay, and then player 2 orders the 3 pieces in decreasing value to in her eyes. Let's say A, B, C. So because player 2 have a different valuation, right? Player 2 may think A is very good, right? B is okay, C is too bad, right? So player 2 will order the 3 pieces in this order, right? In a decreasing value order. And then player 2 will trim, because A is the biggest, he'll trim off a piece called T from A, right? So he cut off a slice from A, right? And so the remaining part of A become A prime. So in player 2's mind, A prime is of the equal value to B. Sorry, try again. So before the trim, player 2 thinks A has more value than B, and B has more value than C, right? So now player 2 has a chance, so that she will trim the piece A little bit, so that the remaining part called A prime will have the same value as B, right, in player 2's valuation. Okay, so then she'll put the T aside. We'll worry about T in a moment. She'll hand A prime, B, and C to player 3. So the cake is smaller actually. What player 3 sees actually is a missing T, right? But never mind, there are 3 pieces. So now player 3 now chooses the most valuable of the 3 pieces, right? A prime, B, or C. Okay? So player 3 will choose first. So choose among the 3 pieces. Okay. Is this all right? Okay, so now player 2 now choose one of A prime or B. Right? So, and she has to pick A prime if it's still available. Okay. So player 3 may pick A prime, and then player 2 has no chance. So then player 2 will choose B. Right? If player 3 choose, say, C, and then player 2 must choose A prime. Okay, so this is the deal. So player 2 now choose one of the A prime or B. And if A prime is available, she has to pick A prime. Because she is the person who does this, right? So in her eyes, A prime and B are the same. So she has to pick A prime if it's available. And then player 1 gets the remaining pieces. Because we demand player 2 pick A prime, so after the action of player 2, A prime is gone, right? So the what left is either B or C. So player 1 will get either B or C. Is round 1 clear? Okay. Player 1 divide. Player 2 do something, right? So possibly he'll trim one piece and hide, or not hide, leave the trimmed piece aside, pass the remaining ones to player 3. Then player 3 choose the trimmed piece and the other 2 pieces. Okay? Then player 2 choose. So player 2 will choose either A prime or B. This is reasonable, right? Because in the player 2's valuation, C is the worst. So for player 2, there's no reason to choose C. Right? So we demand player 2 choose A prime or B because he just trimmed, so that these two, in his eyes, they are the same. Okay? So player 2, after player 2 has done, player 1 will get the remaining pieces. So this is round 1. Okay, so let's analyze the result so that we still remember it. Otherwise, after round 2, round 3, we forget, right? Okay, so let's argue that. So far we have allocated 3 pieces, the A prime, B, and C to 3 players. Now we claim that this actually is an envy-free allocation of the smaller cake, right? A prime, B, and C. Okay, so I want to convince you this is true. After round 1, we have an envy-free division of a cake, maybe with a small missing piece, but the remaining part is envy-free division. Okay, so what's the reason? So player 3 gets to pick, the first chooser is never going to envy anybody because she acts first, right? So because he'll pick the best piece, right? So player 3, definitely okay. Now, player 2, in his eyes, A prime and B are the same value because he just trained, right? And both of them will be more valuable than C because he ordered it this way, right? So whatever player 3 picks, one of the A prime or B will remain. So player 2 just gets that piece of the highest value. So player 2 will not envy anybody. Okay. Now finally, player 1, he's going to get either B or C, right? But these are the original divided pieces, right? Player 1 is the person who cut to A, B, C, and B and C remains. So when player 1 cuts, he must he's ready to accept any one of these. So to him, player 1 think this is fair, right? So this is envy-free. The envy-free division for the possibly missing slice, right? So the remaining part is divided in an envy-free way. So that's okay. The fact we are going to use it in a moment. Okay. So now let's continue. So there's round 2. Okay. So what about this the trim piece, right? Player 2 cut a slice off. So what happened to that piece? So let's assume that it was player 3 who got A prime, right? Because player 3 is going to choose something first. So the A prime either goes to player 3 or goes to player 2. So let's assume it's the first case. The other case is similar. So I leave it to you. So let's just assume player 3 got this A prime. Okay. So the round 2. So we'll ask player 2 to cut T into 3 pieces of equal value in her eyes. Okay, so there's a small slice T, so player 2 will cut them into equal pieces. Okay, so then let the player choose among the 3 pieces in the following order. So player 3 choose first, because we assume, okay, you will see that this is linked to the player who got A prime. So if player 3 got A prime, he will choose first. Okay. So player 3 choose first, and then player 1, and then the last one is the guy who cut. Okay? So that's the algorithm. So now the round 2 is basically the naive divide and the choose, right? So this guy divide, and then we ask these 2 guys choose. Okay? And in that order. So but the choice of divider and the order of choosers are fixed. Must go like this. Okay? Is the round 2 clear? So before we go to next slide, look at it one more time, right? So there's a very, very small slice T on the table. So we ask player 2 to cut them equally. And then we ask the guy who get A prime choose first, player 1 choose second, and player 2 last. So that's round 2. Okay, so now we analyze round 2 to see whether round 2 has any problem, whether it's envy-free or not envy-free. Okay, in round 2, player 3 envies no one because he chose first. I'm not sure whether this he and she is consistent, but whatever. Okay, so player 3 does not envy any because he is the first chooser. So he does not envy anybody. Now, player 2, again, player 2 does not envy anybody because she is the divider. I mean, when she divides, she is willing to accept any of the pieces. So she does not envy, right? This is the problem. The player 1, well, player 1 does not envy player 2 because she picked before player 2. But player 1 may envy player 3 because maybe player 3 get the best piece of this T, the remaining one, right? And player 1 also want that piece, okay? So this round 2 itself may produce some envy, okay? Right, so, but however, so this, the envy is similar to the naive algorithm. So player 3 choose first, player 1 choose second, so player 1 may think player 3 get the better one. Okay, so, but however, we claim that although in the second round, player 1 may envy, but if you combine the whole game, player 1 has no reason to get envy. So here is a claim. Okay, so the claim is, suppose we put the 2 rounds together. This is actually an envy-free allocation for the whole cake, A, B, C. Are you with me? So we have 2 rounds. The first round, we have an envy-free division of slightly smaller cake. The round 2, we divide the small slice, but with a problem, the player 1 may envy, right? So now I claim, if we consider everything together, player 1 has no reason to envy, right? So this is okay. So let's see. So I claim that the algorithm actually is envy-free. Okay. So first, let's make this a simple observation. Right? Suppose someone who is suppose someone who does not envy in round 1, and then he does not envy in round 2, and then he will not envy at all. That's obvious, right? So if he thinks other people get more, it's either get more in round 1 or get more in round 2. So if in both cases he is not envy, then he's happy in the end, right? Okay, so the observation just says that. So I don't. Let me read it. I don't know what. Okay, so given that allocation from round 1 is envy-free, if the division of T in round 2, a player is not envious, and then he is not going to envious when you combine together. This I don't know. This is a rounded way, I mean, to say the simple thing, right? So we have 2 rounds. If a person is happy in round 1, happy in round 2, then he's going to be happy throughout, right? So that's as simple as that. Okay, so therefore, player 2 and player 3 are not envious because they are happy in round 1, they are happy in round 2. So there's no reason to be not happy in the end. Now, the key is player 1. Right, player 1, now the claim is player 1 will not envy the person who has received A prime. In this case, we assume it's player 3. No matter what portion of T that person gets. Remember that because in player 1's eyes, the A union of T is the A, which is the piece he cuts off, right? So player 1 will think the A prime together with T is equal, is of the same value that he got, because he get either B or C, right? So in player 1's eyes, whatever he got actually is equal to A prime union the whole T. Now if this player 3, only get part of T, player 1 would think the total amount player 3 get is less than A, right? It's less than A, which is less than B or C. So therefore, player 1 will not envy player 3, right? So therefore, everybody is happy. This is this is interesting. Okay. Questions or is it clear or? Okay, good. Okay, so now the last algorithm for today. Okay, so now we want to. So just now we divide cakes, right? So we all use knife. I don't know how many times we cut the cake, right? So, okay, so now we want to divide something else, right? Okay, so here is an artificial example. So suppose Mr. Tan, has lots of land, right? So he has land in everywhere. So he has land in Australia, whatever, so A, B, C, I, J, K, okay, whatever. And then he wants to, to leave the land to the children, right? A and B, okay? So then, of course, his children, Annie and Ben, certainly have different subject valuations for the value of the land, right? So now question is, can we help them? Can we tell them, here's an algorithm. This is the way you can divide the land. Okay? Is it clear? So we have 6 objects, and then 2 persons want to divide them. So we want to have an algorithm so that they will have, at least it's a fair division. Okay. So our last algorithm today is called adjusted winner. So this is a procedure which can offer an envy-free solution for the 2 players, right? And the division is so I choose the land because land you can divide continuously, but it's of different nature, right? Because the land are in different places, so it's not uniform, it's not homogeneous, it's heterogeneous, okay. Right? So anyway, so let's look at the problem one more time again. We have 6 pieces of land. We want to divide them between 2 persons, right? That's okay. So the algorithm will have, again, several steps, several rounds. So we are going to do several things. So first, we ask the player, ask A and B to bid. Okay. So because there are 6 pieces of land, so we will give A and B, each person 100 points. Then ask them to bid. Say, it's like you bid for your tutorial or for your course, right? So for this piece of land, I give 50 because I like it, right? So I want to, or you can give 100. Right? So ask them to spend the 100 points to bid on different pieces of land. Okay? So the bidder indicates how much they are willing to pay for the asset, right? Okay, so you can use money or use points. So here, let's say use point. Okay, so let's use the example to illustrate how this. Okay, so each player has 100 points to distribute among the pieces of land. So let's say they evaluate this way. Okay, so I hope this added up to 100, this added up to 100. So Annie will say she likes Australia, so she gives 35 points. And Ben says, oh, only 15 points, right? But now Ben likes Britain, so Ben gives 25 points here, but Annie only gives 20 points, so on and so on and so forth. Okay, so we have 6 pieces, so we ask the 2 players to bid for each of the pieces. But the total amount is 100 points. Okay? Right? So let's say they give this distribution. Okay, here's a procedure. So the slanted font says the procedure, and then the normal font says the example. Okay? So there are 3 rounds. There are a few rounds. So round 1 goes like this. So in round 1, first step, each person is initially allocated the items that they strictly value higher than the other person. I hate this. I copied from book, but okay. So what does it say? So it says, suppose. Okay. So in the example, suppose Anne bid higher than Ben, then Anne get this piece. Okay. So in this case, because Anne gave more points to Australia, so Anne will get Australia, right? So in the second case, Ben gave more points, 25 points, than Anne, so the second points, the B goes to Ben, okay? Now for C, Ben gave 25 points, Anne gave 10 points. Again, Ben gave more points, right? So C goes to Ben. So it's just as simple as that. So whoever give more points will take the piece, right? Now, so in our example, N will get A and J, and Ben gets B, C, I, and K. Okay. So now, not in this example, but in real life or in other situations, theoretically, you can have tied items, right? Both of them give the same number. Okay, so suppose you have a tied item. Now you have to give it to the person with fewer points. Sorry. Let's see. So for example, our example has no tied item. Suppose there's a tied item, right? And then we allocate the remaining part as we did just now. So if they were a tied item, it should go to N first, because if you calculate the pieces, N gets A and J. So N has 60 points. And Ben gets this is 50, 65, 75. So Ben gets more in his eyes. So if there's a tied item, you should go for N. You should pass it to N first, right? And then so on and so forth. So now suppose the point happens to be tied. So just now we say 60 and 75. Suppose both of them are 70. And then it doesn't matter. You can give to any one of them, right? So this step doesn't apply in our example, but it could apply in other situations. So that's round one. Okay, round one is just to divide things based on who give higher bid. Right? More or less it's like this. And of course it's not fair, so that's why we have further rounds. Okay. So round two, if we are lucky, it happens to be fair. Right? If the point total are equal, then the procedure is done. Right? Suppose both of them get 70 points of assets, then done. Right? It's a fair division in both in their eyes. Right? Now otherwise, suppose like in our situation, one person gets 60 points, the other person gets 75. So we have to adjust winner, right? We have to. So this is called adjusted winner. So we have to do some adjust. Okay. So that's round three. So this is the way we adjust. Okay. So the person with most points is the initial winner. And then we calculate the ratio of the initial winner points to loser's point and order the items from lower ratio to highest. Again, this is unreadable, but let's look at the example. So the person with most points is the initial winner. Okay, so in our case, Ben is the initial winner because he has 75 points, right? So now we have to calculate the ratio of initial winner points to loser point and order the item. Okay, so we look at the initial winner, which is Ben. He got B, C, I, K, right? So we have to calculate the ratio of each item in his collection as this. So we'll calculate the ratio of his valuation, his points over N's points. Right? So we calculate the ratio of initial winner's points as Ben's point to loser's point and do something else. Okay, so first let's calculate the ratio. So for Britain, it's 25 against 20, so it's 1.25. And C is whatever, 2.5, I is 3, K is 2. So you do some calculation. So you get four numbers. And then it says, order the items from lower ratio to the highest. Okay, order the items. Lower ratio, 1.25 is lowest. So B is here. And then the second is 2, right? So K is here. And then the next one is 2.5, so C is here. The last one is 3, so I is here. Okay, so this explains the order the item from lowest ratio to highest. The ratio is always bigger than to 1 because this goes to Ben because Ben B is higher than N. So that's why it goes to Ben. Okay, so that's the first step. So you order the items, and then you adjust. So from lowest to highest, transfer items or fraction of items from the initial winner to loser until the point total are equal. Again, this is probably not easy to understand, so we'll do this. So now we need to transfer portions of land in B, right? So we look at this B. We want to give part of B to N so that the points are even. Now we calculate what is the portion of B N should receive. Okay, so we need to transfer a portion of land in B from Ben to N, to Annie. Let X denote the fraction of B that will be transferred to Annie, and then the next slides will tell you how. Okay, so so we want to transfer a portion X of B to N, right? So N originally has 60 points. Now she value B as 20, so she will get X times 20 points after the transfer, right? Now Ben will get something less, right? Ben, if you exclude B, Ben will have 50 points. Now you give a portion X to Annie, so Ben will have 1 minus X remaining. So multiply his value, 25 points, to B. So Ben now has this amount, right? So now we want to set them equal so that we can determine the X. So once you have the equation, you can solve. If you solve, you get the portion X is 1/3. Is this clear? It is possible that you give this 100% to N, and still Ben has a lot. And then you come to the next term, you do the same game. And then you just keep going until you hit the right number. Okay. So in our case, this is one round finish, right? So we determine the X is 1/3. So the conclusion is, so N will get, okay, whatever she gets first, the A and J, and also as the adjustment, she gets 1/3 of B. Now in her valuation, 1/3 of 20 is this 6.67. So total is this number, right? This is 60 and this 66 and whatever. Okay. Now, what is the result of Ben? So Ben originally gets C, I, and K. So this is 40, this is 50. And then he also retained 2/3 of B, right? So which is 2/3 of 25. So that is 16.67. So the total, if you add up, is also 66. So it's the same number, right? So after the adjustment, they all get the same points based on their evaluation. Okay, is this clear? Okay, so now it's not easy to convince you this is a good. This algorithm works. The proof is longer, so I will skip it. But I'll copy the theorem. So the theorem says so it can be done. Okay, so for two parties, so for two players, the adjusted winner procedure produce an allocation, okay, based on this bidding, that has the following properties. So first is equitable. So both players receive the same number of points based on their valuation. So the it's called equitable. It doesn't mean they get, how to say. So it only says in their eyes, because based on their bid, they get the same number of points. So in real life, maybe the values are different. When they bid, they may bid not the true value, right? When you bid your tutorial, you may throw more points, or you may have less, right? So this may not be the true value in the real world, or even the true value in their mind. So this equitable only means as far as the points, the 100 points is concerned, they get same number of points. Okay, so this is property 1. Property 2 says this is envy-free. So neither player will be happier with the other one. So this is because they receive the same points. So they won't envy the other side. And also there's something called, the same Pareto, come again, Pareto optimal. So it says no other allocation arrived at by any means can make one player better off without making the other party worse off. So in economics, there's something called Pareto optimal. It means you cannot improve anymore. If you want to improve one person, you must damage the other person. So there's no way to make them both getting better. So that's Pareto optimal. Now this, according to the theorem, our procedure will produce an answer which is Pareto optimal. So this is supposedly a nice property to have. So we don't prove this, although it's from the example we see that they receive the same point, right? So it's believable. Okay, so I think that's the end for today. Before I finish, so this adjusted winner also assume you could divide the property in any ways, because remember that we have this proportion, x is 1/3. So you have to divide the land in 1/3. It doesn't make sense to get 1/3 of a car, right? So if you want to apply this adjusted winner procedure, you have to assume the object is divisible. Okay. Now, what about indivisible? So like cars and so on and so forth. So that's on Friday we are going to see people have clever ways of dividing them. So we'll see that on Friday. Okay, that's it.